In this video, we'll look at the thermodynamics of adiabatic expansion. Of course, the term adiabatic simply means that there's no heat transfer in any process, so that means that dq is equal to 0. And then in terms of internal energy changes associated with it, because dq is 0, then the internal energy change is due to the work done, so dw is equal to du. Now, we'll note that dW, of course, is defined as negative PdV, as we noted earlier in earlier videos. And if we assume an ideal gas, then we'll also note that dW is always equal to CV dt, even though this is not a constant volume process. The name itself, adiabatic expansion, indicates that volume is changing. So we have to remember that for an ideal gas, we can assume that du is equal to CV dt under any circumstances. But again, remember, this expression and the rest of this derivation will only work for ideal gases. It will not work for a real gas or for liquids and solids. Now, let's first talk about the irreversible case. And of course, we'll set up the appropriate integrals associated with our expression. We're going to be integrating CV dt from T1 to T2 and integrating PdV from V1 to V2. But we'll note when we will assume that our heat capacity is independent of temperature. Again, this is something that's important to note in this particular circumstance. If we have a temperature-dependent heat capacity, what follows will not be correct. So because heat capacity is independent of temperature, and because for the irreversible process the external pressure is constant, we can pull both the heat capacity, the constant volume heat capacity, and the external pressure outside the integral to simplify the integration a great deal. So we get, when we integrate these, just CV delta T is equal to negative P external times delta V. This is certainly one way we can use to calculate the temperature change associated with adiabatic expansion. It is important that we note that temperature will change during adiabatic expansion. If work is done during a process and no heat is transferred, then temperature must change. During an expansion process where the volume is increasing, we will note that the temperature will drop. During a compression process where the volume is decreasing, we will note that the temperature will in fact increase. So just to write that out here, we'll note if delta V goes up, that would be an expansion, then delta T must go down. And that, of course, is due to the negative sign. We will see an opposite effect. And during a compression process where the volume decreases, we'll note that our gas gets hotter. And that should make some sense to you under these circumstances. So that was the expression for the irreversible process. Let's talk about the reversible process. We'll start with the same equation. CV dt is equal to negative PdV, but remember, for the reversible process we assume the external pressure is roughly equal to the internal pressure throughout the process, so we simply substitute the ideal gas law into the equation to get the expression that we have here. Alright. Now, in this case, because temperature is in the expression on the right, in order to integrate, we have to make sure that we get like variables on the same side of the equation, so that we'll need to have all the temperature variables on the left side and all the volume variables on the right. So what we've done here is divide through both sides by temperature to get the expression. Now, on the left we have CV dt over T, and on the right negative NR over V times dV. And of course, in this case, we'll note that we will once again assume that the heat capacity, constant volume heat capacity, is independent of temperature and therefore a constant. We will also assume, of course, that N, the number of moles, and R, the gas constant. So we can pull those outside the integral And when we evaluate the integral with the dt over t, we get the natural log of tt over t1, and dv over v gives us the natural log of v2 over v1. Now, using the properties of logarithms, we can take the CV inside the logarithms by raising tt over t1 to the CV power, and on the right side of the equation we can take negative r, nr into the logarithm, and that would give us v2 over v1 to negative nr, or we can simply reverse the ordering of the v2 over v1, and that would be v1 over v2 raised to the nr, changing the sign from negative to positive. So we end up with this simple expression here relating the temperature change that occurs during the adiabatic expansion to the volume change that occurs during the adiabatic expansion, and it's related to obviously the exponents associated with the heat capacity, constant volume heat capacity, and the number of moles times the gas constant R. Now, if we use the gas law and make a substitution for temperature PV over NR, we get this expression here, where we'll note that NR cancels in the quotient on the left side, and then doing a little bit of algebraic rearrangement, we end up with this expression here by dividing through both sides by v1 over v2 raised to the nr, and then we can associate v2 over v1 and their exponents. Remember, when we multiply a number together, we add the exponents. So this becomes, in this case, CV plus NR associated with the volumes, and then just simply, again, this is just algebraic rearrangement. What we will note here is that we've got P2V2 on one side and P1V1 on the other side. Now, doing a little bit more rearrangement with our exponents here, simply taking the CV root of both sides, which amounts to dividing all the exponents by CV. We end up with this expression here, P2V2 raised to the CP over CV, and is equal to P1V1 raised to the CP over CV. What that means then is that the pressure volume product, where the volume is raised to the CP over CV value, is in fact the same at the end of the expansion as it was at the beginning of the expansion. So this would be after the expansion, P2V2, and P1V1 would be the initial product before the expansion. So we'll note that equivalency here. In this case, and actually I failed to mention that what we're using here is the CV plus NR is equal to CP, as we noted being the case for an ideal gas. There's a nice relationship, and we make that substitution to get this ratio of CP over CV, which, because CP is greater than CV, will always be greater than 1. This is in fact called the heat capacity ratio, and is typically given the symbol gamma for heat capacity ratio. You will find these values tabulated in various sources online, in your text, and other resource texts as well. So you will find the heat capacity ratio is fairly important. As we'll note in the lab, the speed of sound is actually related to the heat capacity ratio of a particular gas. Now, as we noted before, this P2V2 raised to the gamma being equal to P1V1 raised to the gamma indicates that the P times V raised to the gamma is a constant through the adiabatic process. That pressure volume to the gamma product is the same before and after. So we can compare the results of the adiabatic process to that of an isothermal process. In the adiabatic process, we have this PV to the gamma equal to a constant throughout the process. It's called an adiabat if we graph it. The isotherm, For an isotherm, we'll remember that pressure times volume is equal to a constant. So for an adiabatic process, we'll note that P times V raised to the gamma is the same throughout the process. For an isothermal process, we'll note that P times V is equal to a constant, the difference being the exponent gamma. Now, if we graph these, we find that that means, very simply, graphing pressure versus volume, that for the isothermal process, we get something that looks like this. The adiabatic process, because volume is raised to the gamma power here, and gamma is greater than 1, that it falls off faster. And that means that because it falls off faster, the area under the curve is less, which also means that the work associated with an adiabatic process is less than the work associated with an isothermal process. Again, if you think about this, it should make some sense. In an isothermal process, we're getting heat input into the system throughout the process because we need to maintain the temperature. During an expansion, the temperature will fall unless we put heat into the system as the gas is expanding. So in order for it to be isothermal, we have an additional energy input into the system. As a result, we will get more work out. So putting heat in, we're getting more work out. In the adiabatic process, no heat is transferred in during the expansion. The temperature drops during the expansion, and the amount of work that we get out during the expansion will be less. So again, an isothermal process will give us more work than an adiabatic process during the expansion. This will become important, and we'll talk about this in more detail when we get to a later chapter where we talk about heat engines and how they work. So this concludes our discussion of adiabatic expansion and the thermodynamics of the adiabatic expansion. This also concludes our discussion of material discussed in Chapter 2 of our text.